Hello and welcome to Earthquake Tip number 9. My name is Shailesh Kumar Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to understand language to our professionals who are in the field designing and constructing structures, especially architects and engineers. But before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. This earthquake tip number 9 will deliberate on how to make buildings ductile for good seismic performance. Please recall that in the last tip, while explaining seismic design philosophy, it was emphasized that buildings are designed to undergo acceptable level of damages during earthquakes. And for that, ductility is the most important parameter which the building must possess through its configuration, materials, and detailing. So let's first understand how to make building ductile for better earthquake resistance. For this, let us first understand the construction materials being used in construction. Most of the non-urban buildings or low-rise structures are made in masonry. Masonry is generally made of burnt clay brick and cement mortar. However, if you go to hilly regions, you will find stone masonry either with mud mortar or cement mortar. As you can see in this figure 1, in the left-hand side, masonry can carry loads that cause compression, means pressing together, but can hardly take any load that causes tension, means pulling apart. The other most prevalent material is concrete, which is being used in building construction, particularly over last 5 decades. Cement concrete, if I need to explain to you, is made of crushed stone pieces, that is aggregates, sand, cement, and water mixed in appropriate proportion. This concrete is much stronger than masonry, but only under compression. And again, its behavior under tension is poor. In general, we can say that masonry and concrete are brittle and fail suddenly. Remember, I told you in the earlier tip that brittle is just opposite to ductile, and this brittleness is not desirable in earthquake resistant design. Now, to impart ductility, steel is the material which is used in masonry and concrete buildings as reinforcement bars of diameter ranging from 6 mm to 40 mm. These reinforcing steel can carry both tensile and compressive loads. Moreover, steel is a ductile material. This important property of ductility enables steel bars to undergo large elongation, that is the displacement, before breaking. Concrete is therefore used in buildings along with reinforced concrete bars. This composite material is called reinforced cement concrete or simply reinforced concrete, RCC or RC. This is the most prevalent construction material being used world over. However, please note, for earthquake resistant construction, the amount and location of steel in structural member should be such that the failure of the member is by steel reaching its strength in tension before concrete reaches its strength in compression. This type of failure is ductile failure and is preferred in earthquake resistant design. Means steel should fail before concrete. There is a common understanding that too much steel in this RCC building is good for earthquake resistance, which is not true. To understand ductility better, let's understand the capacity design concept through this figure. Let's take 2 bars, as you can see here. This is a bar, 2 bars of same length and same cross-section area. One is made of ductile material and other is made of brittle material. Now let's pull that bar until it breaks. You will notice that the brittle bar breaks suddenly on reaching its maximum strength on relatively small elongation, as you can see in this top graph in figure 2, while the ductile bar elongates by large amount before it breaks down as shown in this bottom graph of this figure. Let me repeat again. Now, amongst the materials used in building construction, steel is ductile, while masonry and concrete are brittle materials. Let's look at figure number 3 now to understand ductility or capacity design through this chain concept. You can see here, this is the chain with links made of brittle or ductile materials. Each of the brittle link will fail just like the bar, as I explained you earlier. That means it will break suddenly with a small elongation. Now let's hold the last link at either end of the chain and apply a force as shown here. The same force F will be transferred through all the links and each link will experience the same force F. If we keep on increasing this applied force, eventually the chain will break when its weakest link breaks. So if ductile link is weaker than the brittle links, then the chain will go large deformation or large elongation before failure. On the contrary, if brittle link is weaker than ductile link, then the chain will fail suddenly and show a small final elongation. So in capacity design, we want to have such a ductile chain and we have to make ductile link to be weakest link. Now let's put this concept of chain into earthquake resistant design of buildings. By now it is clear to you that buildings should be designed like ductile chain. As seen in this figure 4, the common residential apartment construction comprises of multi-storied buildings made of reinforced cement concrete. It consists of horizontal and vertical members, namely your beams and columns. The seismic inertia force generated at its floor level. Remember, I explained you in the earlier tip that due to ground shaking, inertia forces are developed at different floor levels in the building. So this inertia forces are being transferred through various beams and columns to the ground. So the correct building components need to be made ductile. The failure of column can affect the stability of whole building, but failure of beam will cause only localized effect. Therefore, it is better to make beams ductile, weak links than columns. This method of designing RCC buildings is called the strong column, weak beam design method and should be preferred. So if you look at the routine design codes meant for design against gravity loads or any other non-earthquake effects, designer may not be able to achieve a ductile structure. For earthquake loads, special design provisions are required to help designers improve the ductility of the structure. Such provisions are put together in form of a special seismic design code, that is Indian Standard 13920 for RC structure. So remember that adequate ductility can be provided in the members, especially RCC members, where damage is expected through incorporation of special provisions in IS 13920 code. So to sum up, let's have the design with a strong column and weak beams, and these weak beams need to be made ductile by incorporating provisions given in IS 13920. But before we wrap up this tip, let me briefly dwell upon the quality control in construction, which plays the important role in earthquake resistant design. The capacity design concept just explained to you for earthquake resistant design of buildings will fail if the strength of brittle links fall below the maximum assured values. This strength of brittle construction material like masonry or concrete is highly sensitive to the quality of construction material, workmanship, supervision, and construction methods. In a similar fashion, special care is needed in construction to ensure that the elements meant to be ductile are indeed provided with features that give adequate ductility. Therefore, strict enforcement to prescribed standards of construction materials and construction processes is essential in ensuring an earthquake-resistant building. Regular testing of materials on site and at laboratories, periodic training of workforce, and on-site evaluation of construction work are elements of good quality control and must be adhered to for earthquake-resistant construction. That will be all about earthquake tip number 9. You can download this earthquake tip from www.bmtpc.org website. The earthquake tip number 10 will be on how flexibility of buildings affect their earthquake response. Thank you.